Hi everyone, and welcome back to this series of tutorials. I am glad that you are returning back to this series of videos where we are trying to build an end-to-end bioinformatics pipeline using Snakemake. Now, the next series of videos are the most important for this entire series of tutorials because we will begin scripting the workflow, first of all in Bash, and then transferring everything as it is into a Snakemake utility. So in this video, I will start by briefly going through the codes that we will write throughout the tutorial and explaining some of the basic bioinformatics concepts just so that we don't get confused as we write along. Now, in a typical bioinformatics analysis, you will always begin by setting up your directories like I've done here. And then we will begin by accessing your data. And in this case, we will be downloading the raw FASTQ files from the sequence read archives. In most cases, this is data that you already have right from your sequence service provider and in some kind of a flash disk or a storage platform. After downloading your data, the first thing we normally do in bioinformatics is to run a FastQC on the raw data. Now, the FastQC allows us to look at the quality of our reads and possibly guide us into how to trim these reads to have better quality reads. Now, another tool to use instead of FastQC is often FastP. So FastP can give you the quality of your reads, giving you guidance on how to trim these reads, but it can also trim out the reads for you. Now, the next thing after running FastP is always to download and index the reference file. In this case, we will use the wget to help us download the reference file for the human genome, and then we will index the reference file using bwa index. After indexing the reference file, we will then proceed to align our reads to the reference file that has already been indexed. Alignment of reads can be performed using multiple tools, but in our case, we will be using the WMM. After running the WMM for the alignment, the output of the WMM will be a sum file, as you can see scripted here. In the downstream analysis, we can work with a sum file. However, it's always much more complicated to work with, and we will need to convert these sum files into BAM files, which are much more easy to work with and can be easily manipulated. And to convert the sum files to BAM files, we will use a functionality of some tools called the sum tools view. After this, we will need to index and sort the BAM files now. And this step is very much important because when you receive your sequence reads from your sequencing provider, the reads are normally organized in the order in which they were sequenced. Now, accessing this can be challenging. That is why we need to sort and index them. And by doing so, we will basically organize the reads in terms of their genomic coordinates. This basically means that we will have reads that map to the beginning of a chromosome appearing first, followed by the reads that map to subsequent positions along the chromosome. Once we've done the sorting and indexing, the final thing we will do is to call the variants. And here we will use the BCF tools, first of all, creating the mpileup and then transferring the output to the BCF tools call. After calling our variants, the final step we will do is to filter out the variants. We will want variants that have got higher levels of confidence and higher quality. That's the overview of the bioinformatics steps that we will work with throughout the entire tutorial. But one more thing I want to highlight is this script that we wrote here. So as you can see from this script, it's a very long script. It downloads about 7 FASTQ files and runs the bioinformatics functionalities of the analysis for each single FASTQ file. Now, it does so in separate lines. For example, you can see here that we are working with fasterq-dump to process this file, then writing another fasterq-dump for the second file, like so. This is a little bit chaotic because imagine you have almost 100 samples, which is typically what you may be working with. It will mean then that you have a lot of lines of code like this. So this can sometimes be challenging because you can make mistakes and the process will not be reproducible. With a pipeline, for example, what we have here, you can supply this pipeline with any amount of data and it will process it with the same functionalities, the same settings for every single file. So with that said, I will clear everything in my Visual Studio Code right now and I will have an empty directory where we will start all our coding. So as you can see from this screen, I have got a new directory called demo that I will basically use to store all my scripts and all my data. So the first thing I will do is to create new files. as well as install the bioinformatics tools that I will need throughout the analysis. The tools that I will use for these tutorials are stored in our GitHub repository in a document called the toolinstallation.sh. So from this screen here, what I want to do is to basically go to the toolinstallation.sh and then simply copy and paste all of these commands back to my Visual Studio Code. Here, the most important thing I want to do is to create a file called installation.sh, like so, and paste all the tools that I will need, and then open my terminal. If you're working with the Mac, it's just control and a tilde. If you're working with a Windows machine, I think it's something like command and tilde. So I will just clear this to have more space and then start by installing the tools one by one. Now, this command here will simply create for me an environment called Snakemake and then install Snakemake within that environment. One of the easiest way to do that is to simply add a -y that will allow you to seamlessly install that tool without you needing to repetitively enter the -y in your terminal. Since that has been installed, I can now proceed to just put here -y for every command and just copy and paste everything and install them in my computer. So I will simply run that and then just run the remainder of the installations and then start from there. Now, one tool that I forgot to include in this list but is very important is the SRA toolkit. So installing it is pretty much simple. I can just copy and paste one of these commands and then just edit here to SRA tools and just copy this to my terminal. Now I can clear my terminal and then just activate the Snakemake environment, because that is where I will be running all my analysis. So the command to activate your environment is as simple as conda activate Snakemake. There you go, it has been activated. So the next thing I want to do is to create my .sh file where I will be coding the entire script in, and I will just call this advanced.sh, like so. And one more thing I want to copy paste from my GitHub repository are the directories that I will be using to store the various pieces of information I will be receiving from my analysis. So the directories are stored in any of these files. For example, I can just open advanced.sh and just copy all of these lines of code and just paste them there, as simple as that. Those are the only things I will need for this script. Now I will just enter into full mode. So one of the things that we can start is by verifying whether our script is running, and that I will just write a simple echo command here just to tell us it's running, and then come here, clear my terminal a little bit, and then try to run the script. So one of the ways you can run scripts in your system is basically to click here. But for me, I usually prefer to run it from the terminal. And the way to run it from the terminal is always just to provide the path to your bash file. For example, my bash file is in the correct directory and it's called advanced.sh. So if I try to run this, it will throw me an error telling me that permission denied. And why is the permission denied? It's denied because currently I have the permissions to edit this file, but I don't have the permission to execute this file. So that means I will need to change the permissions of this file to include a permission to execute the codes in that file. To change the mode is pretty much simple. We just need to write chmod and then call 775 and just write the name of the script. As simple as that. And then if we rerun the code again, it will tell you running, which is the echo running that we wrote here earlier. So that is that. We can now proceed to start our coding. I will just clear my terminal. Now, the first thing we want to do is to download our FastQ files. And these FastQ files are stored in the sequence read archive. The way to download these files is using the FASTQ-dump or the fasterq-dump from the SRA toolkit. But we want to make this as dynamically as possible to allow us to download as many files as possible. So the easiest way to do this is first of all to set an empty array that we can call accessions. Set it to an empty array, and then have a file where we store the accession numbers. So the accession numbers are currently stored in the GitHub repo in the file called the srr-sec-list.txt. So I will simply go and copy those accession numbers, store them in a separate file, and then provide the path to that file in my bash script. So I will create another file here and just call it accessions.txt and paste my accession numbers there. So I can now read this file into my bash script. I can read it like accessions list and then just supply the path to that file. Copy the path. And then since they all lie within the same directory, I can just delete all these trailing paths. As simple as that. Now, the next thing we want to do is to read this file and then add each and every accession number here to this empty array, such that if we print the accessions array, we can basically just print out the accession numbers as listed. So in other languages like Python, you can simply do something like with open and then provide the name of the file as file, and then do something like for line in file, things like that. But in the bash script, it's a little bit much more different. The thing we want to do here is to write a while loop, and then the connotation is write the structure of the while loop, tell bash script what to do, and then finish with done. So the way to read a file in bash script is just after writing done, you need to point it to the file. For example, here, I need to point it to this accession list variable that contains the path to the file. To do that, I simply need to copy and paste that there. As simple as that. So I will now write the logics of the while loop here. I will write the script and then explain it a little bit much more later. So what are we doing? We are basically just reading the accession list file and then telling the script that while the internal field separator is set to blank, read that file. And then this code here is very much important in our case, because if we remove this code, the program will read our accession list. The final accession number will not be included in our list. If we include this code, then we can be sure that all the accession numbers will be included in our accession array. Now we can confirm that our accession numbers have been successfully added to our accession array by just calling the echo command and then just accessing the accessions variable here, like so. Be sure to include the $sign. And then here is where we can now be much more careful. If we want to access all the elements within the accession array, we need to provide a square bracket and then the @ symbol. This will give you all the items within the accession array. The other thing we want to do is to make sure we put curly brackets that surround the accessions variable. like so. Now we can run this code in our terminal and see whether it prints for us all the items within the accessions.txt file. So you can see that it pretty much prints out every single accession number, and we can play around with this code. For example, what will happen if we remove this line of code here? I'll just cut it out. And I want you to be careful with this accession number here, 6975, because it is the last accession number here. If I run this code again, then you will see that the accession number 6975 is no longer included in our accessions.txt, even though the accession number really exists here. So that is one of the nuances that you need to be very careful while writing your bash script. So I will simply return it to make it successfully run. So at this point, we have included all the accession numbers within our accession array. The next thing we then want to do is to use fasterq-dump to download these FASTQ files in a way that is much more efficient and doesn't require us to manually input the accession numbers in our main code area. So to do this, we can write a for loop that then iterates over every single item within the accessions array and then runs fasterq-dump on every item in that array. So writing for loop in bash script is logically the same as writing bash script in any other scripting language. The logic is basically just writing for something like fq in our array. Remember, for you to retrieve every single item in your array, you need to write it like this with the @ symbol surrounded by the square brackets. So I'll just paste that over there and then tell the program to do, and then just finish with done. Then I can now write my entire logic in the space remaining. So here I want to just run the fasterq-dump, like that, and then simply tell it that I want to download the FASTQ files, but I want them to be split into read 1 and read 2, and we do that by providing the -s functionality. Then I want to supply the accession number, like that, fq, and then point it to the output directory, which we already set up here as the data directory. So I'll just copy that and paste it here, as simple as that, and then ask the program to let me know that the download has started. And also ask the program to let me know that the download has finished. Now I want to try and run this code, and we can see that it will try and download about 7 or so FASTQ files. So the program has started to run and it is currently downloading my FASTQ files. But remember, these are huge FASTQ files. They're almost 3 to 5 gigabytes. For the sake of demonstration for this video, I will reduce the number of files to 2, but you can be sure that regardless of the number of files that you will be adding to the program will be able to process them depending on your compute environments. So I will just stop this run, that is by Control-C, and then reduce the number of accession numbers here to 2 and simply save that. And I will clear my terminal and then just rerun the entire program. At this point, our data has already been downloaded, and we can inspect our data directory to confirm the kind of files that fasterq-dump has given us. If we hover over the data directory, you will realize that the program has downloaded 4 files. We have the files for the first sample, downloaded both as read1 and read2, as well as files for the second sample, downloaded as read1 and read2. That is pretty much why we needed to put this -s here as a functionality. Now, the next step in bioinformatics analysis is to run the FastQC program. The FastQC program will allow us to visualize the quality of the data we have and perhaps inform us whether we will need to do any kind of trimming for our data. Now, remember that we want the quality for each and every data that we have. Here we have about 4 files, so we need the data metrics for all these 4 files. If you had 100 files, then you will need the data metrics for all those 100 files. That is why the bash script code that we saw in the first sections of the video cannot help us here. And at this point, we will now shift to working with a for loop to iterate through this data directory and then run FastQC on each and every of those files. We simply need to write for maybe FQ in, and then we want to access the data directory. To do that, we simply can just copy this here. And just to be safe with our access, we need to put the curly brackets here. Now, this is important because sometimes the naming of the directory could be having some spaces in between them. And putting the curly brackets helps you navigate such circumstances. So remember that we want to access the FastQ files, and the FastQ files have got an extension that ends with a .fastq. So we want to tell the program to access the data directory and then put a / and say that we want all files that end with FastQ, and then tell the program what to do, and then say it's done, and then we can now write the logics of the FastQ program in that space remaining. So with this simple logic, we will not need to write the entire path of the file, but we will just put here an asterisk to read this entire part and just give us the files that end with this name. If at all there are samples that are named like this but do not end with a FastQ, then the program will not return to us those files. The logics for the FastQC program is pretty much simple. We simply need to write FastQC and then tell the program the nature of files we want to give it. In this case, we want to give it the FastQ files, and then point the program to the FastQ files that we want. FQ, because we already initiated the FQ variable here, and then point the program to an output directory to place the results of the FastQC run. So we can simply say -o and then point it to the directory. Now remember that I had already initialized the FastQ directory up here, so I can just copy and paste that directory here and then access it just as we normally access any other variable in bash script. Put a $, and then just put the curly brackets to surround it. And that will be pretty much it at this point. Now, what I will do is, first of all, clear my terminal because I prefer often working with the clear terminals, and then run this code. But before we run this code, we want to be sure that everything is correctly scripted. Now, remember that when running FastQC program, the program will not create any directory that does not exist. So if you have a directory here called the FastQC directory, and we want the program to put the results of the run in this directory, then this directory must be existing before running the FastQC program. That is why we need to, first of all, create the directory using the mkdir program, and just put a -p there and paste the name of the folders that we want to be created. Now, putting a -p here is important because the program will create any parent directory that does not exist, leading to the directory that we intend to create. For example, the FastQ directory has the parent directory as results directory. In case the results directory does not exist, the -p will create it for us. One more thing we need to note is that we no longer need to run the fasterq-dump. If we leave this code as it is without hashing it out, then the program will start downloading the files again. So before running the program, I will hash out this by just doing command / and then just request the program to let me know that the FastQC program is running. And then let it also inform me that the FastQC program has finished running. I also want to hash out this guy and simply run the file again. So you can see that it is now running FastQC, and it is storing all the files here in our FastQC directory. So we will wait for it to run. It doesn't take a lot of time because we only have 2 samples to run. Now our run has finished, and as you can see, the program is letting us know that FastQC is complete. And if we open that folder, we can clearly see that there is a FastQC HTML there, as well as a zip file. The problem with FastQC is that it does not do any trimming for you. So the next thing we want to run is to run FastP. FastP will not only give you the quality analysis of your reads, it will also trim the bad reads from your data. Now, this can be beneficial in very many ways because you don't need to manually interrogate your files to trim the poor quality reads. One more thing that is beneficial with the FastP is that you can manually set how you want your reads to be trimmed. So to run FastP, we need a few files. The first file we need is the read1 file. The second file we need is the read2 file. We also need output files to put the results of the FastP run. This means that we need a read1 out. We also need a read2 out. One more thing we need is a JSON file. If you want this, you can output it. If you don't want, you can just proceed to the other outputs that you may need. And then we also need the HTML file, which is very important because it will help you assess the quality of the files before and after trimming. Now, how do we create these files? The simplest way is to iterate over the FASTQ files we have in our data directory using a for loop, as simple as running for FQ1 in the data directory. So we can just copy paste. Actually, we can just copy paste this entire line of code here because it looks in the data directory. But here, remember that I put here FastQ1. Basically, what I'm saying is I want to start working with these files that are written _1. Now, from the _1 files, I will create the read2 files. So I want to iterate in the data directory, and the files I want are files that end with _1.fastq. So I will remove this dot here. We now no longer need to create any read1 because already we have it stored in our variable here. So we will simply remove that out. Now, to create a read2 from the read1, we simply need to replace this _1 with an _2. How can we do that? We can simply access the FQ_1 as a variable and then put the curly brackets as we normally do and put a / and just say we want to replace the _1 with the _2. Just by running this alone, it will take all files that end with the _1 and replace the _1 with an _2. How do we create read1 out? It's also as simple, but here we want to use a simple technique. Now we want to keep all our outputs in a specialized directory called the FastP directory. If we head over back to the directories that I listed, you can clearly see that I have a directory here called the FastP directory. That is where we want to place all the outputs of the FastP. So I will simply copy this and then say that the read1 output should have the pathway of the output directory. And I can simply do that like this, just accessing the variable like so. And then it should also have a /. And now what we want to do is to create the read1 output by reducing the name of the FQ_1 that you created here using a functionality in Bash called basename. Now, if you run basename like this, if you call basename on any given file, say on this file here, it will read this file and then strip the folder name from that file and just give you the file name and its extension. Now let's try this in the terminal to see exactly what I mean. Let me copy and paste the full path of this file and just clear my terminal and then run basename on this file. The program will strip everything from here and only leave me with this file name and its extension here. And if I run that, you can clearly see that is exactly what it gives me. So if I coin the file path of the FastP directory with the name of the file plus its extension, then I will simply have the full path of my read1 output. To create the read2 output, we simply can just copy this line of code here and place it there. And instead of working with the FQ_1, we can simply write R2 there. Now, to create the JSON file within the FastP directory, the simplest thing we can do is to just run this line of code once again. And now, apply one more tactic. We want the file to end with a .json, but we don't want the file extension .fastq. How do we remove the .fastq file extension? To remove that, we can leverage the utility of basename. If you simply run basename on the full path and include the .fastq, what basename will do is that it will strip the file extension and then just leave you with the name of the file. If I run this, you can see what it gives me. It gives me just the name of the file without the file extension. So that is what we can leverage here with the basename utility. We can just put .fastq. It will read this file, remove this part here, just leave me with this part, which I can now just attach the .json name there. Creating the HTML file is also as simple as that. I can just copy everything here. And then instead of a JSON file, I can just work with an HTML file. Now, remember here that we are leaving the _1 in the file name. And that is not how we want the program to run. We want the program to just have the name of the file, ERR, for example, and then just have a .json or a .html. So you can modify the code here to have _1.fastq and also modify here to have _1.fastq. Now, with that said, we can simply write the functionality of the FastP. And I will first of all write done there. And then write the functionality of FastP as simple as FastP, and then supply it with your first input, which is the FQ1 here. Just copy that. And then just put the output of the read1 file. And the output of the read1 file is the R1 out. So I'll just copy this, put the -o, and then just put the output like so. And then simply put the details of the read2. I put -I this time, and then put the R2, and then put the read2 out. Remember this time it's capital O. As simple as that. And then inform the program that you also want the JSON file to be stored in the JSON file that we created earlier. And you also want the HTML file. Now, just as we did earlier on, we want to hash out the details of the FastQC run. So I will simply hash out these ones just by command / and simply copy this. And just say running FastP and copy that also. And say FastP complete. I will clear my terminal and run the program again. But before I run the program, remember, just like the FastQC program, the FastP will also not create the directory for you. So we need to make the directory before running the program. And it's as simple as what we did for the FastQC. We just need to do mkdir and the name of the directory. Just like this, you can just copy this and put it right there. And then just rename this to FastPDIR. Now I can successfully run the program, and we can see that immediately it creates the directory and it starts to store the output of the run here. I will just reformat these ones and then wait for the program to finish running. Now, at this point, our program has finished running, and you can see it notified us that running FastP is complete. So I will not get into the nitty-gritties of interrogating these files, but what I want to show you is that you can easily go to the FastP directory and then look at the output of the quality check as well as the trimming, and to see whether the program has done everything to your satisfaction. As an example, we can go over one of the HTML files to see what really FastP has done. So if you come here, you will see the FastP report, and that is why we needed the HTML as one of the most important output from the FastP run. And if we scroll down, FastP will let you know what it has done. It will let you know the quality of your files before filtering, and then the quality of your reads after filtering. We can pretty much see here that not so much of quality change has happened, but possibly this could be because the files were, or the reads were of good quality before performing the quality checks or even the trimming. You can scroll down and see how things changed in your second reads with the FastP run. The quality scores are well there. You can interrogate everything here and to see whether things have been done to your satisfaction. Just in case things have not been trimmed well, you can rerun the FastP again using your own specifications in the command line. So let's go back to our Visual Studio Code and then run the next process in the pipeline. Now, the next thing we want to do is to download our reference file and index it. Now, indexing the reference file is very important, as I stated earlier on, because it allows us to randomly access parts of the file without necessarily accessing the entire file. The script for downloading and indexing the reference file is already in the GitHub repo. So what I will do is to just copy and paste the script in our major script here. If you want to know where the script for downloading the reference file as well as indexing it is stored, you can just come to the advanced.sh file and then look for it down here. We can just copy everything here and then paste it in our main bash script. I'll just delete everything here. So this is the script for downloading the file. At the moment, I just want to download the file and not index it. So I will just hash out that. And I will also hash out the code for running FastP, just like that. And save the file and run the program again. Now, my reference file has been successfully downloaded, and you can see that it was downloaded and stored in this file here that ends with the .fna.gz. And if I look back into my directory, I can see that the file name is here. Now I can just create a new directory called I'll create it the base directory here, and just call it ref, and then simply move this file into that folder so that it stays in its correct folder. Now that is important because if you see in my initialized variables here, I had the ref file stored in a directory called the ref directory. So the next step is to just index this file using the BWA index. So this time I will hash out this, and I will simply run the BWA index on the reference file. So I will just clear my terminal and then rerun the program again. But before running the program, I will make sure that I hash out this, because if I don't do that, the program will start downloading the reference file again. So at this point, I can now simply run the program and index my file. And as you can see, the program has begun indexing my master file, and it has started to output some of the outputs such as the .psc file and other more files that BWA index normally output. Now this process takes a lot of time, but at this moment I already have a reference file that I already indexed, so I will simply obtain that file from wherever it's stored in my computer and just use it in my subsequent analysis. Now, the benefits of indexing a reference file is that you only need to do that step once. Once you index your file, you can use it multiple times as long as it is stored in a directory that all these other subsidiary files have been stored. So for my case, I will just kill this process here, clear my terminal, and then obtain my indexed reference file. But then this video is becoming long, so what we will do is that we will complete the entire tutorials in a separate video. So be sure to click on the link in the video description or check in the link at the top of your screen to be able to follow up the rest of the parts. Otherwise, bye for now.